Welcome to the debate. Imagine trying to construct a modern metropolis. You have to lay down the power grid, map out the highways, zone all the commercial districts, and ensure every single building has a rock solid foundation.
Right. And doing that at a city scale requires what? Thousands of engineers, architects, planners coordinating over years and years.
Exactly. Now imagine you have to shrink that entire metropolis down to the size of a fingernail.
Wow. Yeah.
Every road, every power line, every intersection has to be placed with absolute atomic perfection. If two lines cross incorrectly, the entire city essentially burns down. That is the reality of executing an integrated circuit design tapeout. We are placing billions of transistors on a single piece of silicon, but the toll to build that microscopic city is becoming astronomically high. I mean, as the global semiconductor industry races toward a projected $1 trillion valuation by 2030, the cost of designing these chips has just completely skyrocketed. Designing a single chip on a 5 nanometer process now costs nearly $550 million.
Yeah. And we really need to understand where that $550 million actually goes. I mean, it is not just manufacturing materials. The vast majority of that cost is absorbed by massive server farms running simulation compute time, thousands of highly specialized engineering hours, and, well, multi-million dollar lithography mask sets. The barrier to entry has quite literally never been higher.
Right, which means we have arrived at a fundamental inflection point for the industry. Today, we're looking at this $1 trillion semiconductor ecosystem and asking, who actually gets to build it? We are examining the massive shift in electronic design automation, or EDA. I argue that highly automated, open source EDA tools like OpenLane represent the necessary future of the industry. They remove prohibitive financial barriers and solve critical talent shortages by essentially democratizing silicon design.
And I will be countering that premise. Because look, while open source tools absolutely have a role in education and, legacy systems, commercial proprietary EDA tools will remain the indispensable standard. The unforgiving physical realities of modern semiconductor performance demand a level of manual granular control that open source automation just fundamentally sacrifices.
Well, let's break down exactly what is happening in the open source hardware movement right now. Historically, the traditional proprietary model of chip design has been completely financially unsustainable for the broader ecosystem. High licensing costs for commercial EDA tools lock out smaller companies, independent researchers, and academic institutions.
Sure, they're expensive.
Very expensive. But what the OpenLane framework does is genuinely revolutionary. It takes the incredibly complex 11-step physical design flow and abstracts it into a single configuration file. It takes you from RTL synthesis, which is basically the logical blueprint or the code of the chip, all the way to generating the final GDSI file.
The actual physical stencil.
Right, the stencil the factory uses to print the silicon. OpenLane condenses that entire journey into a fully automated flow.
A flow that, I should point out, historically requires a massive team of distinct, highly paid specialists.
Yes, and that is the exact breakthrough. Think about why the software industry exploded in the 1990s and 2000s. It was because the cost of failure dropped to essentially zero. If your software code fails, you just, recompile it. It takes 5 seconds. In hardware, a failed compile like a bad GDSI file sent to a foundry costs $10 million in ruined silicon.
Minimum.
Right, minimum. And that fear of failure is why hardware has resisted open source for so long. But when you pair OpenLane with initiatives like the Google-sponsored multi-project wafer program, which actually allows users to fabricate their chips at a foundry for free, you drop that cost of failure to zero. You give anyone with an internet connection the power to build our microscopic cities.
I hear you. The goal of democratizing hardware is noble, and the community effort behind OpenLane is frankly impressive. But we really have to look at the physics of what we are actually manufacturing here. Commercial EDA tools, the massive suites developed over decades by companies like Cadence, Synopsys, and Mentor Graphics, are the only viable option for high-performance, cutting-edge industrial designs. OpenLane's promise of full automation comes at a very steep cost, and that cost is the loss of granular control.
In what way exactly?
Well, when you look at the empirical data in the source material, Open lane designs typically utilize more logic cells to achieve the exact same function as a commercially routed design.
Okay, which makes the footprint slightly larger, yes.
But it is not just about physical area, it is a cascading failure of efficiency. When you use more logic cells to achieve the same function, you inevitably increase the overall design complexity. That larger physical area dictates that electrical signals just have to travel further. Longer travel distances require more power. More power generates more literal heat. In modern electronics, whether it's a smartphone or a massive enterprise data center, thermal budgets are incredibly tight and battery life is paramount. You cannot simply attach a larger fan to a mobile processor. Those inefficiencies are critical, disqualifying flaws for commercial top-tier silicon.
I see why you think that, but let me give you a different perspective. Look again at the history of the software industry. We moved from writing an assembly language where you controlled every single memory register manually to high-level programming languages like Python or C++. Did we lose some cycle counting precision? Yes, absolutely. A hand-optimized assembly program will always run slightly faster.
Right.
But the massive gain in development speed and accessibility allowed the software industry to scale to where it is today. The hardware industry desperately needs that exact same shift. OpenLane's single-file revolution uses a simple text file to automate floor planning, placement, and clock tree synthesis. I mean, the DARPA IDEA program, which helped fund the Open Road project that OpenLane is built on, had a very specific goal. They wanted to achieve complex system-on-a-chip layouts in under 24 hours without human intervention. By removing the human from the loop, we enable rapid design exploration that simply isn't possible when an engineer has to manually tweak a million individual parameters.
I come at it from a different way because the software analogy completely breaks down when we confront the physical constraints of silicon. In software, if your code is a little inefficient, maybe the program takes a few extra milliseconds to run. The end user rarely notices. In hardware, inefficiency equates to physical space, power consumption, and, as I said, literal heat. Let's look at the physical design flow, specifically detailed routing and static timing analysis, or STA. When you are routing a chip, you are connecting millions of nets using multiple metal layers. It is exactly like a traffic jam in our microscopic metropolis. You have a million cars trying to use one intersection, but you cannot just build a new overpass because the Foundry rules strictly limit you to exactly 7 metal layers.
Right, and the routing algorithm has to solve that crazy 3D puzzle.
Yes, but if you rely entirely on an automated black box algorithm to do this, you inevitably run into routing congestion. These are areas where the density of wires is just mathematically impossible to resolve within the Foundry's rules. In commercial physical design, a human engineer steps in, manually resolves that congestion, and optimizes the critical path to ensure the signal transitions meet the timing constraints. A fully automated approach is incredibly dangerous when you are generating that final GDSII stencil, because if that timing is off by literally picoseconds, the chip simply fails to turn on. It is a brick.
But OpenLane is not just throwing wires blindly into a traffic jam. It uses highly vetted open source tools like FastRoute for global routing and TrittonRoute for detailed routing, applying really sophisticated algorithms to manage that congesting. And it absolutely performs static timing analysis using OpenSTA. It is continuously checking those setup and hold times, ensuring the electrical signals propagate correctly across the entire chip.
It flags the violations, yes, but the resolution of those violations is where the manual control of commercial tools proves its worth. If OpenLane fails to meet timing, your recourse is often to, change top-level parameters in the configuration file, like altering the target density or tweaking the floor plan dimensions, and then running the entire 24-hour flow again, just hoping the automated heuristic algorithm finds a better local minimum this time?
Well,
It is guesswork. In a commercial tool suite, I can manually size up a specific driving cell on the critical path, or manually insert a buffer to boost the signal without disturbing the rest of the meticulously placed layout. That granular surgical control is what separates a chip that runs at 50 megahertz from one that runs at 5 gigahertz.
Okay, the speed difference is a fair point, But focusing entirely on maximizing gigahertz naturally forces us to look at what technology we are actually trying to manufacture. We have to move the debate from how the design is automated to the physical limitations of the silicon itself. Basically, what node are we targeting?
And this is exactly where the commercial tools prove their absolute necessity. The economic value of the semiconductor industry today is driven by cutting-edge technologies. We're talking 5 nanometer, 3 nanometer, and 2 nanometer processes. Commercial vendors integrate these cutting-edge technologies rapidly. They work directly with foundries like TSMC to model extreme parasitics. At 5 nanometers, the wires are so unimaginably close together that electrons can literally jump across the gaps.
Quantum tunneling.
Exactly. Quantum tunneling, you aren't just managing basic electricity anymore. You are fighting quantum physics. Commercial tools contain the massive algorithmic power necessary to predict those quantum jumps and model the intricate multi-patterning lithography rules required at those scales. Open source tools, by contrast, are currently limited to much older process design kits, or PDKs. They primarily support Sky 130, which is a 130 nanometer process, and GF180 MCU, a 180 nanometer process. You cannot design a competitive AI accelerator on a 130 nanometer node.
I'm not convinced by that line of reasoning because it assumes the entire semiconductor market is exclusively chasing the bleeding edge of physics. Not every device on Earth requires 2 nanometer monolithic integration. I mean, think about the Internet of Things. Think about medical devices, industrial sensors, and the automotive sector. These industries heavily rely on older, highly reliable, mixed signal nodes like 130 nanometer and 180 nanometer.
That's true, but
A smart refrigerator or a tire pressure sensor does not need a $550 million 5 nanometer chip. In fact, using a 5 nanometer chip in a car's braking system would be a massive, absurd waste of resources. Furthermore, the Sky 130 PDK is a massive milestone in engineering history. It is the first manufacturable, free-use PDK ever released. It has already resulted in hundreds of successful tape-outs. The open-source model is proving its viability in the real world right now, serving a massive segment of the market that commercial vendors simply price out.
well, it is proving its viability for simple microcontrollers and academic projects. But to say it serves a massive segment of the market ignores where the actual revenue and the strategic geopolitical power in semiconductors actually lies. The source material explicitly points out that TSMC alone accounts for about 50% of global semiconductor production, primarily because they absolutely dominate the advanced nodes. If you are using open source tools limited to 130 nanometer, you are effectively playing in the sandbox while the actual industry is building skyscrapers. The OpenLane flow is fantastic for a basic RISC-V single-cycle processor or a simple peripheral module, but try designing a high-performance multi-core processor with incredibly complex clock tree synthesis requirements. When you have to route a clock signal perfectly evenly to a billion different transistors so they all tick at the exact same picosecond, the limitations of the open source router and placement engines become glaringly apparent.
Calling it a sandbox drastically underestimates the trajectory of open source development. Open source communities iterate at a blistering pace, but more importantly, the extreme complexity you are describing at the 5 nanometer node highlights a massive vulnerability in your argument.
Oh, really? How so?
If the industry relies exclusively on proprietary commercial tools to navigate those quantum physics, who is going to be left to actually operate them?
The specialized engineers trained by the industry.
Engineers that currently do not exist. According to the industry surveys in the source material, talent acquisition and retention is the #1 strategic priority for semiconductor executives today. The numbers are frankly terrifying. We are looking at a projected deficit of 67,000 technical workers in the United States alone by 2030. The European Union is trying to build a pipeline of 500,000 microelectronics experts just to meet the manufacturing goals of the European Chips Act. Where do those people come from? Universities cannot effectively train a massive influx of students if they have to pay prohibitive licensing costs for commercial EDA tools which can run tens of thousands of dollars per seat. Students end up sharing highly restricted lab time, or worse, they learn the theory of chip design on a whiteboard without ever executing a physical tape-out. Open source tools and free PDKs like Sky 130 are the only scalable educational solution to build this talent pipeline. It allows any student anywhere in the world to design a chip, run the RTL to GDSI flow on their own laptop, and actually understand the physical design process without being locked into a single vendor's ecosystem.
That's a compelling argument. But have you considered the actual quality of the education that student is receiving? If a student is trained exclusively on OpenLane, a highly automated tool where you essentially push a button and a Python script orchestrates the entire synthesis, floor planning, and routing process, they are not learning the rigorous manual optimization required by top-tier foundries. Do they truly understand the underlying math? Do they understand how to manually fix a setup time violation where the clock period must be strictly greater than the clocked queue delay plus the propagation delay plus the setup time?
Hold on. Let's break that down for a second. You just listed a massive timing equation that sounds incredibly intimidating. For anyone not building chips in their garage, what you are really saying is that the electrical signal has to settle down and become stable before the clock ticks and the quote-unquote camera takes the picture, right?
Yes, exactly. That is the contamination delay and setup time. If the signal is still fluctuating when the clock ticks, the chip records garbage data. My point is, an engineer needs to know how to fix that manually by resizing individual transistors. If they're used to a tool that just auto-resolves or ignores the finer details of that timing, they aren't actually doing engineering.
But OpenLane generates comprehensive, human-readable reports at every single step of the flow. The timing reports, the power analysis, the layout versus schematic checks, it is all right there in the directory structure. A good educator uses the automated flow to show the student the big picture of the microscopic metropolis and then digs into those specific log files to teach the underlying physics of why the signal arrived late.
Reading a log file is very different from manually intervening in a layout to fix a design rule check violation. I mean, if we train an entire generation of engineers to treat physical chip design like a simple software compilation process, they will be utterly lost when they step into a commercial foundry and have to shave picoseconds off a critical path on a 3-nanometer design. Furthermore, relying on open source tools introduces a massive liability for commercial tapeouts.
A liability?
Absolutely. With commercial tools, if there's a critical bug in the routing algorithm that is causing a short circuit in your design, you pick up the phone, call the vendor, and they provide a dedicated patch because you pay for that enterprise support. With OpenLane, you are replacing vendor dependence with a reliance on a fragmented community for tool reliability and bug fixes. When you are preparing for a tapeout that costs millions of dollars in mask sets, you cannot rely on a random open source GitHub pull request to fix a critical physical verification error.
Calling it a fragmented community ignores the reality of modern open source development. There are over 8,000 active enthusiasts, academics, and professional developers constantly refining the OpenRoad and OpenLane ecosystems. The collaborative model actually ensures that tools are rigorously tested across a much wider variety of edge cases than a closed QA team in some corporate office might even imagine. When someone finds a bug, the community fixes it, and everyone benefits immediately. And let's not forget the DARPA funding behind this. This isn't just hobbyists hacking away in basements. It is a concerted effort by major research institutions to establish a robust general-purpose hardware compiler. The goal is to elevate the baseline of hardware design so that a defense researcher or a small startup with a brilliant idea can achieve complex system-on-a-chip layouts efficiently.
We are moving toward a world where the market differentiation is in the architectural idea itself, not in who has enough venture capital to afford the software to route the metal layers.
Look, architectural innovation is crucial. I won't argue that. But in silicon, the architecture and the physical implementation are inextricably linked. You cannot divorce the RTL from the GDSII without sacrificing performance. The physical design, the floor planning, the placement of macro cells, the intricate tuning of the power distribution network to prevent voltage drops across the chip, that is the engineering. OpenLane provides default configurations for things like power grid pitch and offset. But as the source material details, When you integrate complex macro cells like an SRAM memory bank or a custom arithmetic logic unit, you still have to manually configure the power hooks, the voltage and ground nets, and the routing layer restrictions. Even in this supposedly fully automated tool, the uncompromising physics demands manual granular configuration.
But doing that in a transparent, human-readable text file is fundamentally more accessible than navigating a labyrinth of proprietary graphical interfaces and undocumented commercial scripts that require years of specific vendor training just to understand.
Accessible, yes, but optimal? No. And in the global semiconductor industry, suboptimal chips simply do not survive the market.
Well, I think it is time we summarize our positions. My stance remains that open-source automation frameworks like OpenLane are fundamentally necessary for the future of the semiconductor industry. They shatter the financial barriers that have historically kept hardware design locked in the hands of a few massive corporations. By abstracting the incredibly complex physical design flow, they are the only viable, scalable way to solve the existential talent bottleneck we face, training the hundreds of thousands of engineers we desperately need. Through community-driven innovation and free-use PDKs like Sky 130, we are democratizing chip design and paving the way for a massive influx of creativity in hardware.
And my summary is this. While open source tools like OpenLane serve a fantastic educational purpose and are perfectly adequate for trailing edge nodes, they cannot replace commercial EDA tools. The unforgiving physical realities of advanced silicon, the power density, the extreme thermal constraints, the quantum tunneling, and the timing margins at single-digit nanoscales require the granular control and rigorous manual optimization that only commercial software can provide. Peak performance requires absolute precision, not just rapid automation.
I think we have both highlighted valid points today. There is a very clear inherent tension between accessibility and peak performance in semiconductor manufacturing. OpenLane brings incredible speed and democratization, pushing the cost of failure down to zero, while commercial tools offer the absolute optimization required to push the boundaries of physics at the bleeding edge.
Yeah, and examining this dichotomy really deepens our understanding of just how incredibly complex the RTL to GDSI flow is. Whether you're using a single file configuration or a massive proprietary enterprise suite, mapping logical code to physical silicon remains one of the most challenging engineering tasks on the planet.
And there is so much more to explore in the source material regarding the specific intricacies of physical design. You know, like the deep dive into macro cell placement, standard cell libraries, and how SRM memory arrays are actually laid out in the physical silicon.
Oh, absolutely. We barely scratched the surface of clock tree synthesis algorithms and the intricate math behind static timing analysis constraints.
Which means there is plenty for our listeners to weigh for themselves. As always, we aren't here to declare a winner. We are here to illuminate the blueprints of that microscopic metropolis. When you think about the future of that tiny billion-transistor city, you have to ask yourself, will it be built exclusively by a closed guild of master architects, or will its streets ultimately be paved by the collaborative effort of an open world? Thanks for joining us.